Welcome to this video on Newton's third law. So let's see, what did Newton say? First in original Latin and then the English translation. To every action there is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. Here, this part on two bodies is extremely important. The action is acting on one body and the reaction is acting on the second body. So when we state Newton's third law, we should not abbreviate as every action has an equal and opposite reaction. This abbreviation is incomplete. Newton was very precise when he stated the third law, and so should we. What is missing in this abbreviation is the core idea in Newton's statement: two bodies. Action is acting on one of these two bodies and the reaction is acting on the other body. People always ask a wrong question, which is, if every force involves an equal and opposite counterforce, why don't the force and the counterforce cancel each other out? The answer is, you forgot the two bodies part. The force and the counterforce act on two different bodies. Hence, there is no cancellation. So what are the forces on a body? First of all, we have to remember that a body cannot exert a force on itself. Only an external agent can apply a force on a body. The examples of external agent are gravitational force, electric force, magnetic force, force applied by attaching cables and rods, force applied by pins, clamps, bearings, ball sockets, hinges, etc. A force applied by putting bags of sand or boxes of metals, or by sitting on a body. The force applied by neighboring bodies that are in contact. This may include friction. For example, when you put a large box on the floor, the large box and the floor are in contact. One of the contact force acts perpendicular to the floor on the body, and that force is equal to the weight of the body or the box, and the contact force from the floor cancels out its weight and the box remains in equilibrium. But now if you try to push the box on the force, you will feel some resistance. That is the friction force. Also, force applied by gears, wheels, rack and pinions. For example, the force applied by the gear on the wheel of a vehicle makes it spin. Let's explore this action-reaction a little bit more. So here what we have is a rod which is in equilibrium under two forces, 2,000 pound here, and 2,000 pound here. To view the action-reaction forces, we need to cut this blue body into two pieces. One is a green body and the other is an orange body. So if we cut through the blue body somewhere here and separate the two pieces out, the green piece and the orange piece, then you expose the action-reaction forces that are equal and opposite. 200 pounds, 200 pounds. So the green piece of the body is in equilibrium, and the orange piece of the body is also in equilibrium. The purple forces acting on two different bodies are the action-reaction pair of Newton's third law. Let's look at a little more complex situation. So here, instead of just one 200-pound force here and one 200-pound force there, we have added a couple of other forces. 80 pounds up, 30 pounds up, 110 pounds down. So there is a up-down equilibrium. 80 plus 30 cancel out the 110. And there is a left-right equilibrium, 200 pounds and 200 pounds. As before, we cut this blue body into two pieces. Green piece and orange piece. The green piece is in equilibrium. This 30-pound is an internal force. 200 pounds is an internal force, and this 150-pound foot moment is an internal couple. And now you see that the green body is in equilibrium. Similarly, the orange body is also in equilibrium. 30 down, 30 up, 200 left, 200 right, and 150 pounds moment. The purple forces and couples acting on two different bodies are the action-reaction pair of Newton's third law. A second look at action-reaction. The purple forces and couples came from the equilibrium of the green body and the orange body. So why call them action and reaction? What is orange body's action on green body? What is green body's reaction on orange body? Let's explore these two questions. So here is the orange body, and here is the green body. Now we are going to find out what is the orange body's action on the green body. And we do that in several steps. First, we transmit this 200-pound force to here. Then we transmit the 30-pound force here. And just because we move the 30-pound force parallel to itself through a distance of 5 feet, it adds a moment of 150-pound foot. So now, if you compare the diagram of the green body that you see here with the diagram that we saw in the previous screen, you will see that the orange body's action on the green body actually establishes the equilibrium of the green body. Second question, what is the green body's reaction on the orange body? Step 1. This 200-pound force, which is pointed towards left, we transmit that as a 200-pound force going towards left. We transmit the 110 pounds force parallel to itself by distance 3 feet. So 110-pound force ends up at the left edge of the orange body. And just because you moved it parallel to itself by a distance of 3 feet, you add a couple of 330-pound foot. Next step, we transfer the 80-pound force to the left edge of the orange body. And just because you have transferred this 80-pound force through a distance of 3 feet plus 3 feet, 6 feet, it adds a clockwise moment of 480-pound foot. So if you combine this 330 counterclockwise with 480 clockwise, you will get a net couple of 150 pound-foot. And now if you look at the green body's reaction on the orange body, you will see that this green body's reaction on the orange body actually establishes the equilibrium of the orange body. Thank you for listening.